I'm going to be solving number 30, and it reads, a bead of mass m equals 5 kilograms is released from point A and slides on the frictionless track shown in figure 5.3. Determine A, the bead's speed at points B and C, and B, the net work done by the force of gravity in moving the bead from A to C. So the first thing that I wanted to do was first I wanted to, it asks for the bead's speed at points B and C. So the way that I did that was I kind of set up an equation where at point B you see that it's right there. So at that point it has potential gravity, gravitational potential, and it's also moving. So there's also kinetic energy. So the way I solved for the speed was I had to isolate K, which is the kinetic energy. And to do that, I have to know the total mechanical energy of like the system because there's no non-conservative force acting on it. So the way that I did that was I solved for the total mechanical energy because it's conserved by using and starting at point A, which is right over here. So at this point, there's only gravitational potential because it says it's released at that point, meaning that it starts from rest. So that means that there's no kinetic energy. So the way that I did that was at point A, you can see that the total mechanical energy is equal to, but then since there's no kinetic energy, cross that out, and then you can see that the mechanical energy equals mgh, and I'm going to call the height in this case as h1, and h1 is supposed to be 5 meters, so let's just say h1, and I'm going to make a key over here, so h1 equals 5 meters, h2, meaning the height at point B, is 3.2, h3, the height at C, is 2 meters. Yeah, that way I don't have to worry about numbers throughout the entire problem. So, now moving on to the actual question. So, you want to find the bead speed at point B and C. So let's start with B. So again, like I said, mechanical energy, or like energy, is conserved because there's no non-conservative force. So I just set the total energy at point A equal to the total energy at point B. So that's just mgh1 equals K, which is the kinetic energy at point B because it's moving, plus the gravitational potential energy at that point because again it is still above the ground, because h0 is at the bottom of like the roller coaster thing. So yes, so there's still gravitational potential, so that's my equation. And again, you want to solve for the speed, so you want to isolate K. So then what I did was I did K equals G, and if you subtract it over, it becomes this, and then you want to solve for V, and the way you can do that is, again, writing out what K is, or what kinetic energy is, which is 1/2 mv squared. Okay. And again, we should also probably put subscripts because that's the velocity at point B, but we also have to solve for point C later, so just to make it clear, I'm calling it V1. So then V1 velocity at B. So then when I solve for v1, it becomes 5.94 meters per second. Okay, so that's how you solve for the speed at B. And then for the speed at C, this equation doesn't change. So you can just use that equation and plug it in, but use the different values for in respect to C. So then in that case, it would be v2. So v2 I called the velocity at C. So then so then v2 equals square root 2g. But in this case, I set the initial mechanical energy, so the mechanical energy at point A equal to that of point C, because again, it's conserved throughout the system. So that way, instead of it being h1 minus h2, you have to change that to h1 minus h3, because you're going from here to here, and that's h3. So then if you just change that, you can still keep the equation that you solved for in the beginning, which saved you a lot of time. And then I solved for it, and I put it in the calculator, and it was about 7.67 meters per second. Okay, so that's how you do part A. Part B, it asks for the net work done by the force of gravity in moving the bead from A to C. So the way I did that was, it's a law that, or like, I don't know if it's the work energy theorem, that the change in kinetic energy is the net work done. And because there is no other force except for like the force of gravity, because it says it's frictionless, so there's no friction, and the only force that they mention is gravity. So you can just assume that the only force, or the net force is gravity. So then that means that the change in kinetic energy is equal to the net force, and then in that case, that's just equal to the work done by gravity. So then you just have to solve for that. The change in kinetic energy, again, so it starts from rest, and then they ask you from part A to part C. So then if it starts from rest, and the final velocity is, or the final kinetic energy we can solve for, because the change in kinetic energy is final kinetic energy minus initial kinetic energy, it's essentially just equal to the final kinetic energy. So, yeah, you just have to solve for the final kinetic energy, or the kinetic energy at part C. So, yes, that is equal to 1/2 m, 7.67 meters per second. I got this from this right here, because that's the velocity at point C. And then it's minus 0 again, because it starts from rest. So then when I put that into the calculator, I got about 147 joules. So that's how you solve number 30.